Our two study areas, which Dave is going to describe in more detail in a few minutes, are Mason County and the American Bottoms. Mason County is a little farther north, so the groundwater is, which is, the temperature is about the mean air temperature, is a little less than 14 degrees C. The American Bottoms, which is down by East St. Louis, is about a half a degree C warmer. These are the temperatures that Xinli is going to use in his calculations, which he'll tell you about after Dave's part. Be either closed loop or open loop. Closed loop systems can be either horizontal, as shown in this slide. The water, or actually the heat transfer fluid, never contacts the ground. The heat transfer is through the walls of the tube. This slide shows the cooler fluid coming out. Here's your heat pump. Comes out, flows through the tube, gets gradually warmer, so it exchanges heat with the ground, gets gradually warmer, and then goes into the heat exchanger, and it's used to heat the building in the summer. It can also be used to cool the building, heat the building in the winter, and it can be used to cool the building in the summer. So that was a horizontal system. Here's a vertical system. Don't try to read the text. It's not important. A vertical system uses a well that's drilled just for heat exchange purposes, and there's a tubing loop in the well. Open loops use groundwater. Heat is either dumped into or extracted directly from the groundwater. This slide shows a two-well system. Water is pumped from one well through the heat exchanger and then re-injected in another well. In practice, these wells are kept as far apart as is practical. And in areas with abundant groundwater, you can have just one well pumping groundwater to the heat exchanger, and then it can go to a drain. This shows it going to a stream. In 2004, when this data were published, there were approximately 45% systems were vertical closed loop, 35% horizontal closed loop, and the other 20% were open loop systems. So I'm going to turn it over to Dave now, and then at the end I'll have some concluding remarks.
Thanks, Tom. Well, my focus for this project was on groundwater resources and how they relate to the open loop geochemical or geothermal applications. And the question that I dealt with is, can groundwater availability with respect to open loop groundwater heat pump systems be evaluated using existing information? Or are there other information and data needed in order to do this? One thing that became apparent in my, as this progressed, was that the heat content of water is one of the things that's typically ignored when groundwater is evaluated as a source of water. Usually it's for a domestic well and the heat content of that water is not part of the use. And so this is something that I think there's some work that can be done here to kind of make this a little more practical and more commonly used. So the data I use, the existing data, are geologic and hydrogeologic information. Use that to delineate and locate the aquifers. Hydraulic information, which I use to characterize the aquifer properties. Groundwater quality, Tom will be touching on that. And then groundwater use is an indicator for how prolific or productive the aquifer is. And my sources of information are the water well records that are on file at the State Geological Survey. They're available online through the Geological Survey's webpage through something called IL Water, there's a link on the front page for that. I looked at a number of publications from the State Water Survey and the State Geological Survey, and I also looked at some of the unpublished data on file at the two agencies. Now, this was a statewide effort, but in order to kind of reduce the scope and make it more practical, we chose two pilot areas. From my perspective, the selection criteria were it needed to have a prolific aquifer, something that provided abundant water, and also that there was a wealth of information about the subsurface. So using the statewide map that the State Water Surveys published on the estimated potential yield of sand and gravel aquifers in Illinois, we kind of came up with two pilot areas. The estimated potential yield, as you can see, is the orange color over here is the highest potential yield, and there's an area down here also. The other aquifers that have a little lower estimated potential yield are shown in this color here. Just to give you a statewide perspective, this is the Muhammad Aquifer, and there's some aquifers that run up the Illinois River Valley. This is the Green River Lowland. So one of the areas that we chose for a pilot was Mason County. It has a prolific aquifer. It's typically a rural setting, and so that way we could look at agricultural applications of geothermal applications in this groundwater heat pump. And then the other one that we looked at is down in Madison and St. Clair counties. This is an urban setting, so we were able to look at commercial and industrial applications, and there's also kind of a unique groundwater quality problem down there. The American Bottoms is located in southwest Illinois. It's a floodplain. The Mississippi River borders it on the west. There's a bluff on the east that's formed by a bedrock high with glacial deposits over top of that. The width is 2 to 9 miles, and it's about 30 miles north to south. The bedrock surface underlying the floodplain is a relatively flat, undulating surface that has an incised channel in the middle of it. This is important because it identifies the thickness of the sediments that underlie that floodplain. So you take land surface and you subtract bedrock surface and you get the thickness of those sediments, which down in this area are mostly sand and gravel with lesser amounts of silt and clay. The maximum thickness is 171 feet up there, reported in a borehole up in this location here, but in general it's about 100 feet thick to 120 feet thick. It thins considerably to the east along the bluff. Now, what's important for groundwater resources is something called saturated thickness, and this is the thickness of the material that is full of water. The pore spaces are full of water. And in this area, that thickness varies with the rise and fall of the water table. But in general, it's about 100 feet thick over most of the floodplain, the American Bottoms, and it thins, of course, towards the bluff on the east. The American Bottoms is kind of a unique location in geologic history. What this map shows is the extent of the ice sheets in the last glaciation called the Wisconsin. And these ice sheets were down here until about 20,000 years ago. So we have ice sheets that were in Illinois, Wisconsin, Minnesota, and into the Dakotas. Well, these ice sheets are producing enormous volumes of meltwater. And the meltwater flowed south from the ice sheet margins along these paths that are kind of in this yellow color. And as you can see, the American Bottoms is kind of the focal point for that discharge of the meltwater. Carried along with this meltwater are huge volumes of sediment, ranging from clay to silt, sand, and coarse gravel. And the sediments that are down here in the American Bottoms were deposited by this meltwater. And that's what gives the highly productive aquifer down here. Transmissivity is a way of measuring the capacity of the aquifer materials to transmit water. And so the higher the value, the greater the transmissivity, the better the aquifer is. And so in the American Bottoms, the transmissivity high is down here at about 300,000 gallons per day per foot. And it falls off, of course, towards the boundary on the east side. Water use in the American bottoms peaked in 1956 at a little more than 110 million gallons per day. Most of this water was used in industrial purposes, and as that use declined, what happened was that the potentiometric surface of the aquifer in the American bottom started to rise. And in some cases, it has risen to the point where dewatering wells are necessary to keep certain stretches of the interstate system from flooding. And the amount of water that's being pumped is about 15 million gallons per day. So you can see that the aquifer in the American bottoms is a very prolific aquifer. Turning our attention to the second pilot area, Mason County. Mason County is located on the west end of the Mahomet Aquifer, which is a highly productive aquifer that stretches from the Indiana state line across central Illinois to the Illinois River over here. Mason County, the land surface is mostly sand and gravel, indicated in this color here, except in the southeast corner, which is a lot of silt and clay that was deposited by the Illinois glaciation from 125 to 180,000 years ago. So in this area, the sand is from land surface to bedrock, and this is called the Havana lowland. The bedrock surface has valleys just like the American bottoms, but it's a little bigger. It's the Mackinac Bedrock Valley, and it's downstream of the confluence of the Mahomet Bedrock Valley and the Mackinac Bedrock Valley. So you have this as the main feature of the bedrock surface. Remember, the thickness of the materials is land surface minus bedrock surface. Those bedrock valleys were part of the pre-glacial drainage system, and these existed 2 million years ago. The Mackinac Bedrock Valley is part of the ancestral Mississippi drainage that was over in this part of Illinois prior to glaciation. And the Mahomet Bedrock Valley is part of drainage that came in from Indiana and possibly Ohio. The thickness of the sediments that are in Mason County are as much as 300 to 400 feet, where the land surface is high. And the saturated thickness is, again, where the water table is and down to the bedrock surface. And a saturated thickness in Mason County ranges from a little less than 100 feet to almost 200 feet. So we have a thick aquifer. Is it prolific? Is it a very productive aquifer? Well, we can judge that by the number and distribution of high-capacity wells. A high-capacity wells is a well that pumps around 800 to 1,000 gallons a minute. These are the irrigation wells in green, and the red are municipal wells. In 2012, there were just a little more than 2,100 irrigation wells in Mason County. And the amount of water that was pumped for the irrigation season was 98 billion gallons of water. So we have a very productive aquifer down here as well. So we've got our 2 pilot areas. So what do we have? We have 2 areas, pilot areas, that are underlain by prolific aquifers, very productive aquifers. The reason for doing that is that we wanted to make sure that the amount of water that's available for this application, the open loop heat pumps, was not limited by the yield of the aquifer. So that was one of the variables that we controlled by making sure it was a highly productive aquifer. Another thing that we kind of found out was that a lot of these areas, these 2 areas in particular, have a lot of wells. That are either in use, they're unused, and some of them are abandoned. And this is kind of a hidden benefit, because one of the major costs for implementing heat pump systems is the cost of installing the well. Well, if you already have the well there, you're kind of halfway home.
Okay, in this project, I mainly worked on the heating and cooling potentials of the using groundwater heat. Groundwater source heat pump system. My work mainly consists of 4 parts. I'm going to talk about that one by one. This diagram shows the groundwater source heat pump system model that we used for our calculation. The diagram here on the left This diagram shows the system in heating mode, and that on the right it shows in cooling mode. The top part is the heat pump device itself, and this part in the middle is the groundwater heat exchanger, and the bottom part is the groundwater well. So when the heat pump is working in heating mode, groundwater and the supplied heat to the buildings. So when it working in the cooling mode, it actually operates in reversely. It sucks the heat from the building and dumps the heat to the groundwater. These are the 5 typical energy balance equations of the heat pump and heating mode. These are the 5 equations in cooling mode. We haven't got enough time to talk about that in detail, but I really want to talk about the CEOP here in each mode. Here are the definitions of the CEOP. In heating mode, it's defined as the heat capacity over the electric power input. What does this mean? This means if you suck one part of the heat from the, if you input one part of the power of electricity, you can suck the quite amount of heat from the ground or from the groundwater. If CEOP equals 3, that means if you input one part of electricity, you can suck 2 parts of the heat from the groundwater. In our calculation, the range of CEOP is shown here. For the open loop system, in heating mode, we used 3 to 4, and in the cooling mode, we use 3.5 to 6.7. And in this study, the groundwater supply temperatures we used for both heating and cooling modes is 15 degrees centigrade, as Tom mentioned before. And for the return temperatures, it is 10 degrees centigrade for heating mode and 26 degrees for cooling mode. This slide shows the weather data we used for Mason County. HDD here means the heating degree days, and the CDD is the cooling degree days. This is the data we used for American bottoms. To estimate the heating requirements of the single-family house, we used 2 models here. The one is the Lawrence Berkeley model. The other is the Moore-Page model. In both models, heating load was calculated first, and then the monthly average pumping rate of the groundwater was determined. For Mason County, we used both models and calculated the required pumping rate. We considered both 1-story and 2-story houses. You can see here. And we can see that there is a very good agreement between the 2 models. This is the calculation result for the American bottom. We also carried out a sensitivity study on heating and cooling requirements for the 2-story family houses. In heating mode, the value we used is 2, 3, and 4, the value of COP. And in cooling mode, it is 3, 5, and 7. Yeah, we estimate the monthly average well production rate required for each house is based on the weather data and also choosing the COP values, as I explained. This figure shows the sensitivity analysis for Mason County in heating mode. We can see that the maximum well production rates occurred in January here, less than 3 gallons per minute. This diagram shows the similar result obtained for American bottoms. This is the calculation result for cooling mode. This slide shows the sensitivity analysis for Mason County cooling mode. The maximum pumping rate required occurs in July, which is about 3.5 gallons per minute. And this diagram shows the result obtained for the American bottoms in cooling mode. We estimated the heating and cooling potentials of the 2 studied areas, as David explained before. One is Mason County area, another is American bottom area. By choosing the highest monthly pumping rate, that is 3.5 gallons per minute, and using the documented pumping rate at each area, we estimated the total number of the houses using groundwater source heat pump in each studied area. This table shows the estimated numbers of the houses that can be supplied by the groundwater source heat pump in each studied area. In American bottom, it's about 7,000 houses, and in Mason County, it is more than that, and it's about 25,000 houses there. This table shows the estimated ground heating and cooling potentials in each studied area. In Mason County, it is 3.8 times 10 to the power 12. The unit is kilojoules per year. And in American bottom, it is about 1/4 of that in Mason County. And the total is 4.79 times 10 to the power of 12 kilojoules per year. What does this number tells us? I did a calculation, and this potential equals 1.3 times 10 to the power of 9 kilowatt hour. And I compared that with the power production from the UIUC's Abort power plant. My calculation shows that this total heating and cooling potentials is about 3 times the electricity generated each year, assuming that all the turbines at this power plant were to run continuously for a year. I also checked that the real power generation in 2005, the real power generation from this power plant is much less than that. It's actually this much. It's about 20,000 megawatt hour. Sorry, this should be megawatt hour. And that means this total heating and cooling potentials is about 57 times that electricity generated in 2005. So that gives us some general idea about how much this heating and cooling potential is. Now we can see that the groundwater has great heating and cooling potentials, which is a great source for heat pump applications.
I'd like to add that those peak pumping rates shown in Xinli's graphs, about 3.5 gallons per minute, are easily attained by an ordinary water well that's installed in thousands and thousands of homes in Illinois. Groundwater quality can affect heat pump operation either through deposition of a layer of calcium carbonate. This is sometimes called scaling or fouling, This isn't a heat pump, it's a hot water line, but it gives you some idea. Certainly, a homeowner should never let their system get that far scaled up. The other problem is, the potential problem is corrosion. I'll just have a few things to say about fouling. I won't say anything about corrosion today. Lucky you. Here's a graph showing the reduction in heat transfer efficiency. I think that's what the author meant by energy loss. For thin films of calcium carbonate, both in inches and in millimeters. So for example, for pure calcium carbonate, 5/64 of an inch or 2 millimeters would reduce energy, the heat transfer efficiency by about 5%. That's something a homeowner, for example, could live with in 1 year, but certainly you wouldn't want to let that build up year after year. I'll have more to say about that in a minute. Calcium carbonate solubility depends on lots of factors. Fortunately, I don't have much time, fortunately for you that is, so I won't go through that. Just to mention, there are things that we can easily measure and calculate. And what I'm going to be showing is the results of calculations, not the details. One thing I should point out, though, is that calcium carbonate is one of the few salts whose solubility goes down as temperature goes up. And so scaling or fouling is only going to be a serious problem for cooling with groundwater, not heating. So let's go back to this graph. I took slightly more than the maximum pumping rate from Xinli's modeling, assumed the median amount of calcium carbonate precipitated for Mason County water, and made some other assumptions. And in a typical cooling season, mid-May to mid-September, I estimated that you can get about 1 millimeter film deposited on a heat exchanger, which translates to between 2 and 3% loss in heat transfer efficiency. This isn't going to be a serious loss, but a homeowner would want to get his or her heat pump cleaned out, say at the end of the cooling season before you switch over to heating. It can be a problem, but I don't think it's going to be a serious problem. Okay, now to switch over, just throw out a few more factoids to finish the presentation off. As of 2009, the report was published in 2010, there were roughly 600,000 systems, both closed loop and open loop in the country. That may seem like a big number, but it's actually less than 0.5% of the single family houses in the country. If we could retrofit a significant number of homes, and this report said, did the calculations for 20% of single family homes with a ground source heat pump, we could reduce both primary energy use and CO2 emissions by about 9%, and that's a significant effect. And also peak electrical demand in the summer by about 11%. So we could have some serious impacts on energy consumption and CO2 emissions by using ground source heat pumps. This slide has two graphs from a recent paper about heat pump use. This was for European countries. I couldn't find a comparable one for the US, but two things really stand out on this for me. First of all, the adoption of heat pumps seemed to have been very rapid. They really grew from between 2000 and 2008. The left-hand graph is for absolute savings in millions of tons of CO2 compared to if these houses and buildings had been heated by fossil fuels. The other thing that really stands out is while many of larger countries, France and Germany, for example, had their savings in the 200 to 300,000 ton range, Sweden seems to have really gone to ground source heat pumps in a big way. They're on an absolute basis, they're over 1 million tons CO2 savings per year. On a percentage basis, it really stands out. By 2008, they'd been over 35%. Finally, just an example of a large-scale system here in central Illinois. This is the Mahomet IGA store. They do all of their refrigeration with groundwater heat pump. Their flow rate, 150 gallons per minute, would be equivalent to a small town of about 1,000 people. But they happen to be in a very favorable place where they can get the groundwater out without affecting neighboring wells. This slide is from a presentation that was given at ISTC a few years ago. Anybody who's interested in this can access it. It's available online at the ISTC website. So, as both Dave and Xinli have said, ground source heat pumps have a great potential for application in Illinois. There can be some serious savings in energy and CO2 emissions. That's it.
So thank you very much. We have time for a few questions, if anyone has them.
Was there concern in the American bottomlands about other groundwater contaminants in that area?
I'm sorry, Dave. What was your question?
Was there concern in the American bottomlands about other contaminants in the groundwater, toxic substances?
We didn't look at that. The dewatering wells that Dave showed, we have taken, the water survey has been helping IDOT with their dewatering wells. We have analyzed water samples, and there doesn't seem to be anything hazardous, but the water does have a lot of dissolved stuff in it. There could be serious scaling and corrosion problems. That's a big industrial area, and certainly there are some places where we probably want to just leave the groundwater where it is in that area.
Was the groundwater temperature not cold enough where you didn't have to run a compressor?
I think we'll let Xinli answer that question. Was the groundwater not cool enough that you didn't have to? Yeah.
Heat pump over the air-based heat pump is that the groundwater temperature is almost constant for the whole year. So it's good for you to use that in both heating and cooling mode. That is an advantage. For example, in summertime, the air temperature is very high. It is not that efficient for you to dump the heat to the air, but if you dump the heat to the groundwater, it's much easier because temperature is lower than the air. And during wintertime, the air is very cold. It's colder than the groundwater. and it's much easier for you to absorb, suck the heat from groundwater than from the air.
Yeah, I'm just saying, this is the groundwater.
Yeah, as long as it's constant. So we need a constant groundwater temperature.
Are you asking, is the temperature such that you can practically run a heat pump?
Yeah, I'm saying if it's like 45, 50 degrees, you probably don't even need a compressor at all.
I guess you know more about heat pumps than I do. You're probably right. I think Xinli had addressed that before he actually did his modeling. He made sure that the temperature is in a range that would be feasible.
Are there any other questions? Okay, then thank you to all three of you. And I'd like to again thank all of our speakers this morning for their presentations. We're now going to adjourn for some networking time, and then lunch will be served at noon, and that's in the River F room. If you go back down the hall, turn to the right, you can look at the various tables of displays, and then River F is there on your right. If you look at your name tags, your table is marked on those, and then you have a color code for your lunch choice. They'll be coming around and asking you then and bringing you your lunch that you chose from the menu earlier. Also, for those who may be leaving at this time or right after lunch, we have a box for recycling your name tags. If you could put those in the box if you not going to take them with you, we'd appreciate it.